All right, graphing exponential and log functions. I would agree that exponent graphing is fairly easy. Yes. Log functions, I would not label that easy. We'll see why in a minute. We do have asymptotes coming up, transformations. Okay, but it's our first time graphing one of these, and pretty much anytime the first time you do something on a graph anyway, what's your go-to method if you don't know what a graph looks like? Okay, put it in the calculator. Fair enough. What if you don't have a calculator? A table. Let's make a table. So we'll make an XY table. Now our first one, so we may not know exactly what the best things to plug in are. So I'll just tell you that -1, 0, and 1 are good options to plug in. Because, what's 3 to the -1? 1/3. Let's just do all of these, and then we'll put them all on the graph at once. 3 to the 0, and 3 to the first, 3. So we sort of just built our parent function. We'll use this over and over again. -1, 1/3, 0, 1, 1, 3. Thank you. Now that's going to usually be enough, but since this is our first one, maybe it would be good to do 2 more just to make sure we understand what's going on. Again, generally speaking, 3 points is enough, because once we've done a bunch of these, we'll know what the shape looks like, and we don't need a bunch of points. But this is our first one, so let's do 2 more. What's 3 to the -2? 1/9. So yeah, how exactly do you graph 1/9 without bumping into the x-axis there? I don't know. Speaking of gets really close, that sounds like an asymptote. So if we plugged in -3, we'd be at 1/27th, and then 1/81, and then 1/243, and then I forget the powers of 3 after that. But you're getting closer and closer to the x-axis. What kind of asymptote is that? A horizontal or vertical? Horizontal asymptote at y = 0. All right, back on the other side of things, what about 3 squared? 9. So that fits on the graph. What would 3 cubed be? 27. That's like not even off the graph. That might be off the page. So that's way up there. So by doing this set of numbers, -1, 0, and 1, we usually capture the turn, like right where it makes the turn, because it's super flat and then it's super steep, and that -1, 0, 1 is right at the spot where it makes the turn. No transformations on that one because that is the parent function. Okay, well, just like a parabola, is 1, 1, 2, 4. Like you could graph a parabola pretty quickly and pretty easily, I think, based on those parent function points. We kind of need to know these points, and you don't have to memorize them because you can figure them out. Just like a parabola, you could square 1 and square 2. Here you can do the exponent and figure out the points, but we need to know those points because we're going to use that table like everywhere else, because we're going to graph by transformations. There is no horizontal or vertical asymptote. You're right. I mean, it gets really steep, but it never gets infinitely steep. It can keep going. Right? You could plug in x = 5 or 10 or 20. You'd get really, really big numbers, but it keeps drifting to the right. So, number 2. What do you think the transformation is? right 2. So this is why we teach transformations, because now, once you know the parent function, the transformation rules are the same. So yeah, this is right 2. So I'm going to put kind of a crosshairs at right 2, kind of my new starting point there, my new origin. And then I don't need to come up with a table again. I already have the table. So I'm going to use the same table, but I'm just going to start from my new origin. Right? So it's the same set of, careful, I guess they're not points anymore. They're more like directions from the starting point. So I'm still going to go, I kind of boxed the weird thing here because I need the y values. Left 1 and up a third. But not from the origin, from the new origin, the new starting point. And then 0, 1, and 1, 3. And again, those will be the 3 key points I'm looking for. We did those extra points on the first one just because we hadn't seen this graph before. But now we know what it looks like. 3 points, again, those specific 3 points always capture right where the turn happens. It's only number 2, but Logan, how about vertical or horizontal asymptote? Good. Nick, a vertical asymptote? None. Good. So if you know transformations, which you do, and you know them pretty well, like this is one graph, we're just moving it around. Number 3. Don Trey, I fashion you as a transformation expert. What's that plus 2 going to do to the graph? Move it up 2. So again, I'm going to put a little bit of a new origin on there, a new starting point on there. And why don't you try this one? Take that same set of points, start at this origin, and put those points on there. Allie, how about the horizontal asymptote? I moved my graph up 2 spots, y equals 2. Jackson, vertical asymptote? None. So be careful with the horizontal asymptotes. It didn't change on that number 2, but that's because we moved it left-right. So that didn't change where the horizontal asymptote was. You could move that left-right and it doesn't change. But when we moved the graph up 2, that bumped that horizontal asymptote up 2. And you don't have to highlight it. Some people like to kind of help them see what's going on. All right, number 4. Again, same graph, different transformation. Ethan, what's that 2 out front do to a graph? Stretches it. Reese, that's right, but more specifically, what is it, or how do I use the 2 in my table here? Good. So it's that same process. There's a 2 out front. It goes to the y values. So 2/3 and 2 and 6. So we didn't translate. We didn't move anywhere. We just stretched. Carla, how about the horizontal asymptote? Good. Didn't go anywhere. Still y equals 0. Jack, the vertical asymptote? There's not one. Yeah. What do you think number 5 does? What's that plus 3 do? Left 3. So why don't you try number 5? Okay, number 6. Number 6. Jack, I think your answer was right. How did you get that? I'm just curious what you did.
When you plug in -1, it flips the 1/3 to be just 3.
Okay, so you just kind of rebuilt the table?
Yeah.
That's completely okay. So you recognize that, wait, this is not the same graph as what we had, so let me just redo the table. Nothing wrong with that. Nothing wrong with that at all. Plug in -1, you get 3. Plug in 0, you get 1. Plug in 1, you get 1/3. Yeah, that's fine. It's not how I was going to teach it, but if that's how you see it better, then let's go with that.
How are we going to teach it?
I'll show you that in just a second. So let's finish it off this way because I like it. It's right.
I didn't draw it too. I just kind of thought it through.
Okay, nothing wrong with that. Like just be like, oh, that's new. Let me just do a table, and maybe just in your head, and then realize, wait a minute, that's flipped. What's another way to write 1/3? Here's how the math teacher was going to overcomplicate things. 3 to the -1. So I could have written this as 3 to the -1 to the x, which would be 3 to the -x. And what does a negative on the x do? Flips, but not up and down, flips left and right. And that's what we got. We changed the x signs of the original, and that's our graph. So you could see it either way. You could do this kind of trickery and realize that it's a left-right flip, or you could just kind of start from scratch and be like, well, you know what, that's new, that's different, let me just plug in some points. Either way. Okay, so that wasn't too bad, right? Hey, we're halfway done. Number 7. Let me ask a question that I think I know the answer to. Do you prefer logs or exponents, just generally speaking? Me too. So instead of working a log problem, let's work an exponent problem. So how could I turn this thing into an exponent problem?
Log of y, or 3 to the y is x.
I could do my fishhook thing. Right, that gives me an equivalent statement. So 3 to the y equals x. Okay, so things feel like backwards now because I've got x equals instead of y equals. But it's an exponent rather than a log. So I feel like it's worth the price of dealing with x and y kind of backwards than having to mess with logs. Let's do a table. Although this table is going to feel weird because x and y are kind of backwards. So instead of picking x's to plug in, I'll pick y's to plug in. And based on what we just did, what do you think would be good y values to plug in?
-1, 0, 1.
Let's see, 3 to the -1. Wow, these are familiar looking values here. Well, it's not the same thing. How is that table different than the tables on the...
Y equals x.
The x and y's are flipped. Hey, there's a mathy name for when we flip the x and y. Starts with an I.
Inverse.
Inverse. So that means, what we kind of already knew, exponents and logs are inverses of one another. So this graph is going to be the inverse of the exponent graph. Okay, over 1/3, down 1. over 1 up 0 over 3 up 1. And we could do that same stuff with the 2s and the 9s, but we did it once. We kind of got the feel of this. Like 9, 2 would probably be on this graph, and then 1/9, -2 would be on this graph. No transformations, that's the parent function. Liam, what do you think for a horizontal asymptote? But it goes up past y equals 2. I mean, it flattens out, but it's still going up. Y equals 2 would say that there's not an asymptote right there because it's going to go north of 2. It's kind of a trick question I gave you. Like it keeps going up, so there is no horizontal asymptote. Luciana, how about a vertical asymptote? Y equals 0 would be this. X equals 0. So it's sort of like our horizontal and vertical asymptotes traded places, but we switched X and Y, so that makes sense. Kind of the same thing from here on out. There's our parent function table. Now we'll just move that thing around all different ways. It's a crazy thick book I gave you. Number 8, x minus 2 in parentheses. Ryan, what's that minus 2 doing, like transformation-wise? I think it's going to go right 2. So I'm going to put my new starting point right 2. And then I'm going to use the same table of values, but I'm going to start at right 2. So over a third down 1, over 1 up 0, over 3 up 1. Sketch in my log graph. And then ask Cody for the horizontal asymptote, which there's not one. Kennedy, how about the vertical asymptote? Good, x equals 2. We moved it over, so x equals 2. Nicole, number 9, what's that 2 out front going to do? I mean, that's not wrong. That's not really what I want to do, but it's not wrong. Think about transformations in graphs. If there's a 2 out front, what does a 2 out front usually do to the graph?
Stretch it by 2.
Stretch it by 2. Now, what you said was right, but if we did that, we'd probably have to rebuild the table and start again.
Yeah.
So that's not wrong. Like, you are allowed to put it there, but then we've got a new function and we'd have to restart our table. So let's keep our table and just know that that 2 out front stretches by 2. And since we're stretching by 2, I'm going to go ahead and copy that table down. Preston, what do I do with the 2 in terms of my table to accomplish a stretch of 2?
Multiply y by 2.
Good. Multiply the y values by 2. So -2, 0, and 2. So 1/3 -2, 1 0, and 3 2. Thank you. Carson, how about a horizontal asymptote? None. Rena, how about a vertical asymptote? Good. I'm still intrigued by Nicole's suggestion right here. It works, right? If you plug in 3, log base 3 of 3 squared, that's log base 3 of 9. Well, 3 squared is 9, so you get 2. So I think that's the long way around, but it's still accurate. It worked. Oh, looking at number 10, this is kind of tricky. That plus 2, is that an up 2 or is that a left 2 situation? Up 2. Cole, why is it up 2? Why did you say up 2 rather than left 2? Perfect. It's not in parentheses. Like as opposed to number 12, which is in parentheses. So that's an up 2 situation or transformation. So I'll put my new origin up 2. I already have the table. You can rewrite it if you want to, but you can just look back at it, especially since you don't need to change it. Third, -1, 1, 0, 3, 1. Aaliyah, how about the horizontal asymptote? Not 1, correct. Cooper, vertical asymptote?
X equals, which one is that? Oh, X equals 0.
X equals 0. Alright, I think I'll leave the last 2 for you to do, but we can kind of peek ahead. We sort of answered 13 already. Which functions are inverses?
Log.
And exponents. So I'm going to say like 3 to the x and log base 3 of x. So like those are the specific ones, but you're right, if you would have just said exponents and logs, that's more generic. Also correct. Why? What would your answer be? Like, why are they inverses? X's and Y's are switched. Okay, so this landed on a good day. But hey, you got world history tomorrow. That's it. That's 2 more. I'm leaving you to do 2, but I think you can handle that. Multiply the y's by 1/2, and then move it over to the. Which way is number 12 going? Almost said the wrong thing here. X plus 3 is left 3.